welcome to 2014 midterm review. This is so exciting. We're ready to start. Before we start though, Miss Blunt's class, we need to change our locations. We are no longer in the gym. If you are period 3, you are going to be in D136. If you're in period 5, 6, you're in room D134, and if you're in period 8, 9, you're in D132. Again, please note the changed locations. Period 2, 3, you're in D136. Period 5, you're in D134. Period 8 in D132. Do not forget to be at the gym, to be at school at at by 11:45, especially if you need a calculator, and to be in the classroom by 12 o'clock ready to take the test. Bring 2 to 3 sharpened number 2 pencils, 2 to 3 blue or black pens, and a scientific calculator. You can also bring water if you need it. So we're going to start by going over math of chemistry, significant figures. Remember, the easiest way to remember significant figures is to think of a map of the United States. If the decimal, you remember A, Atlantic absent, and PP, Pacific present. If the decimal is absent, you start from the Atlantic side. If the decimal is present, you start from the Pacific side. Let's look at the examples. In this first example, there's no decimal. Go to the Atlantic side. Go in till you find a number that's not a 0. Every number thereafter you count, 1, 2, 3, is significant. So there's 3 significant figures. In this second example, there is a decimal present. So we go to the Pacific side. We go in until we find a number that's not a 0, and every number thereafter is significant. 1, 2, 3. All of them are significant. The 3 of them are significant again. In the next example, there is no decimal. Go to the Atlantic side, go in till you find a number that's not a 0. Count every number thereafter, 1, 2, so there's 2 significant figures. If the decimal was present here, 150 point, we'd go to the Pacific side, go in until we find a number that's not a 0, and count. That would make 3 significant figures, not 2, like in the example when the decimal was absent. Finally, the last example, the decimal's present. Go in until you find a number that's not a 0. Count every number thereafter. 1, 2, 3, 4, 5. There are 5 significant figures. When you're calculating, you always round to the lowest number of significant figures from your knowns. So, for example, if you're calculating the density of a metal sample weighing 10 grams with a volume of 3.7 centimeters cubed, and you want to find the density, the first thing you want to write down are your knowns. In this case, your knowns are 10.0 grams, and a volume is the mass, and volume is 3.7 centimeters cubed equals the volume. You can look at the reference tables. You can look at table D if you get confused as to what the units are for mass and what the units are for volume if you ever need help. Then we know that we are given mass and volume, and you are looking for, in this case, density. Well, where could you go to find the density formula? Table T. Table T states that the density formula is density equals mass over volume. In this case, what you're going to do is you're going to divide 10.0 divided by 3.7. Now we want to round to the correct number of significant figures. What we do is we count the significant figures of both of our measurements. The decimal's present, so we go to the Pacific side, go in and count every number thereafter. So there's 3 in this number on top, and then in the number on the bottom, there are 2 significant figures. And then we round to the least number of significant figures. So what we are going to do is we are going to round our answer to two significant figures. So if we divided 10 divided by 3.7, you end up with the number 2.70. We want two significant figures. It's the Pacific side. Go in 1, 2. Go one step further. Go one place further. So instead of the tens, go to the hundredths. If that's 5 or more, raise the score. 4 or less, let it rest. So your answer in terms of significant figures would be 2.7 grams per centimeters cubed. Two significant figures in your answer. Next, what happens if we want to find the volume instead of the density? Well, our knowns are the same again. Our knowns are, in this case, our knowns are the density, which is 1.5 grams per centimeter cubed, and a mass of 200 grams. But this time we're looking for volume, so that's our unknown. So we're looking for, we don't know what the volume is. We use the same formula again, density equals mass over volume, but this time we substitute in a little differently. We have 1.5 equals 200 divided by the volume, which becomes x. In order to solve this problem, we have an equal sign. We need to cross multiply across the equal sign. We get 200 equals 1.5x. Now we're going to divide both sides by 1.5, divide by 1.5, and you get 200 divided by 1.5 equals 133.3, and its volume centimeters cubed. Now if we're looking for the correct number of significant figures, we see that 1.5 has two significant figures and 200 has three. Don't get confused, there is that decimal there, so start from the Pacific side, go in every number thereafter. So the least number of significant figures is 2. So this is kind of confusing. In this case, there'd be two significant figures, but you can't change the value. So the answer would be 130 centimeters cubed, because on the Atlantic side, we'd go in until we find a number that's not a 0 and count significant figures. But that still approximates the value of the 133.3. Now, just a word of warning, pay attention to the significant figures when it asks. If in doubt, write down the answer that you are most comfortable with, that you know is correct, so that you can show that you did your math correctly. You don't want to round incorrectly in the end and cause problems for yourself unless you're asked to. During an experiment, a lab group calculated the percent composition of oxygen in magnesium oxide to be 45.5%. The accepted value is 50%. Calculate the percent error. Well, in this case, we're not looking for density anymore. Now, where we are given, we're given a measured value. This is the measured value right here, this 45.5, and we're also given an accepted value. If you look on table T, you can see the formula is percent error equals measured value minus accepted value over accepted value times 100. So you would substitute in the measured value, 45.5, minus the accepted, 50.0, divided by 50.0 times 100. If you're asked for a correct numerical setup, don't forget to include the times 100. When you subtract, make sure you press the enter key on your calculator and then divide and multiply by 100. And in this case, you should get 9%. Okay, 9% error. You could have come up with a negative number, which is fine. All that means is that the measured value is lower than the accepted value, or you can just take the absolute value. Either way is fine. Okay, the next few types of problems, math problems that you're going to see, well, you'll see a temperature conversion. Again, all math, go to table T. You need to convert 32 degrees Celsius to Kelvin. We write down the formula. Kelvin equals degrees Celsius plus 273. We have 32 plus 273 equals Kelvin. And so we add them together and we get 305. Is that correct? Having a hard time doing math in my head on the board. The answer is 305K. If it gives you the Kelvin, don't forget to make degrees Celsius the X. Now, a little bit of theory. You need to know the law of conservation of mass and matter and how it relates to balancing equations. We're going to see two examples on the next slide. But remember, the law of conservation of mass or matter states that matter or mass cannot be created or destroyed. It can only change form. So we're going to see how this applies to balancing equations and to solving mass problems. Okay? Oh, I have a slide. Oh, here we have balancing equations. Let's look down at the bottom of the slide first. What we are going to do is we realize that by the law of by the law of conservation of matter, we know that you cannot create or destroy matter. So that means we have to have the same number of atoms of each element on the reactant side. Remember, this is the reactant side, as we have on the product side. This is the product side. This is what's produced. So let's look at this example. We can take an atom inventory, or you can just balance by inspection. If you take an atom inventory, you write down the numbers, each element, the names, the symbols for each element, and then you write down the numbers of each element. 3 carbons, the number of atoms, that's the number of atoms of each element. And this is complicated because now you have 2 oxygens and 1 oxygen gives you 3 oxygens altogether. So let's start let's start with the carbons. We have 3 carbons on this side. We only have 1 carbon on this side. So let's put a 3 in front of carbon dioxide to give us 3 carbons. That will balance out the number of carbons. It also changes the number of oxygens, but I'm going to hold off on that for a second until I balance the number of hydrogens. I have 8 hydrogens on the reactant side. I have 2 on the product side. In order to get 8, I'm going to put a 4 in front of the water. That gives me 8 hydrogens. Now I'm going to figure out how many oxygens I have. Well, I have 3 times 2 is 6 oxygens as part of this carbon dioxide, the 3 carbon dioxide molecules or moles, and I have 4 oxygens as part of the water. So in order to get a total number of oxygens, I add them together. So I have 10 altogether on this side. How can I get 10 on this side? I put a coefficient. This is a coefficient of 5. That represents the number of molecules or moles of molecules of oxygen. That's different from this little number that's like a submarine. That's a subscript that's written below the element and tells the number of atoms. So the subscript tells the number of atoms and the coefficient tells the number of molecules. Now, before we go on to the mass problems, we're just going to look at the different types of equations that there are, the different types of reactions. You have to be able to recognize the different types of reactions. So the first reaction is synthesis. Synthesis is like a marriage. You can recognize it because you have 2 elements or 2 small compounds that come together to produce only one product. So I like to call a synthesis reaction a marriage. Decomposition is the opposite. Notice you start with a compound and it gets broken down into 2 smaller substances. That's like a divorce. Single replacement, you always look for somebody all by themselves on either side. If you have somebody all by themselves and a compound, you would notice that this is single replacement. The one all by himself is like the teacher going to replace the kid in the relationship like we talked about in class. So single replacement, you need to have a single guy. And double replacement, we call the wife swap. By wife swap, we mean that the cations switch places. So if you notice in silver nitrate that the silver and the nitrate are paired up, but look in the product side, the silver is paired with the chlorine from the NaCl. And the sodium, which was originally paired with the chloride ion, is now paired with the nitrate. So the cations switch places. So your double replacement is the wife swap. We actually have one more type of equation or reaction that we have to identify. This last type of reaction is written down here where it says balancing. You guessed it. This is combustion. How do I know this is a combustion reaction? Because you have a hydrocarbon, which is carbon and hydrogen, reacting with oxygen. It always needs to have oxygen in order for it to be combustion to produce carbon dioxide and water. Okay, so we talked about balancing equations in terms of the law of conservation of matter. Now when we turn the page, I'm going to skip the next page and go to this page quickly, and then we'll go back. We are going to look at determining missing mass. Remember the law of conservation of matter? Another similar law, similar name, is the law of conservation of mass. That states that mass cannot be created or destroyed. It can only change forms. So right where the yield sign is, you're going to put an equal sign because you know that the mass of the reactants has to equal the mass of the products. So it's asking us how many grams of iron, so we don't know the grams of iron, are needed to react with 8 grams of oxygen. Notice the grams. This is a mass problem. Okay, to produce 28.9 grams of Fe3O4, or interesting. That's a very strange formula. Doesn't really obey the law of conservation in the law of definite proportions, but we're going to just ignore that for right now. Remember, there's really only one way to write a formula, and this one way would not be correct. So let's actually change this. We're going to say that this is iron 3. So if this is iron 3, it would be iron plus 3 and oxygen minus 2. Cross out the charges, crisscross the numbers, you get iron 2 Fe2O3. So let's put that there, and we'll balance it another time, but let's just make sure that you understand that. The balancing doesn't really matter for this because all we need to worry about is the masses of the reactants need to equal the masses of the products. So we add X plus 8 to get the mass of the reactants, and we set it equal to 28.9 to get the mass of the products. Subtract 8 from both sides, and we get X equals 20.9 grams. Law of conservation of mass, we have 28.9 grams when we add the reactants together, equal to 28.9 grams when we add the products together. Now, this is different from mole ratios. Notice the word moles, not mass, in this particular question. It says, according to the reaction, what's the total number of moles of sulfuric acid needed to react completely with 5 moles of aluminum? Okay, so we don't know the number of moles of sulfuric acid. You probably don't know, but H2SO4 is sulfuric acid. I'm going to write that over here. That's sulfuric acid. So we don't know that. That's X. Needed to react completely with 5 moles of aluminum. Well, so what this is saying, if we looked at the balance equation, the mole ratio between aluminum and sulfuric acid is I need 2 moles of aluminum to react with 3 moles of sulfuric acid to get these products? Well, I don't have 2 moles. Instead, I have 5 moles. So, and we want to know how many moles of sulfuric acid we need to react then. So we need to set up a proportion. We write 5.0 divided by 2 equals x over 3. So the coefficients are on the bottom, and what we're given is in the numerator and our x. Anytime we have an equal sign, we cross multiply. We get 2x equals 15. We get x equals 7.5 moles. Notice the difference in the mass problems and in the mole problem. Remember the mole ratio, if you're looking for the mole ratio of the substances in the balanced equation, you're looking at the coefficients. Okay, energy and bonding, I just went back a slide. Okay, energy and bonding, sometimes when you're given a balanced equation, there's going to be heat or energy or kilojoules in the equation. So for example, if I have H2 plus O2 yielding H2O, and I balance it, and I balance it, I realize I have to put a 2 here, so I have 4 hydrogens and 2 oxygens. I need the 2 oxygens because it's on this side. I need to put a 2 here in front of the hydrogens, so it's now balanced. And in this case, this is an exothermic reaction. So I'm going to write plus heat. Heat is on the product side in this case because the reaction is exothermic. Therm means heat, exo means released. So if heat is released, it's in the products. Now, if you think about it, you would also realize that if you were feeling an exothermic reaction, heat would be exiting the reaction or exiting the beaker, and you would feel hot. That's the opposite as if you felt cold. If you feel cold, the opposite is happening. Instead of heat being released, you have heat leaving your hands, which are warmer, going into the reaction. So in this case, we have heat, therm, going into the reaction. And if heat is going into the reaction, we put the heat on the reactants side of the balanced equation. So say we have carbon plus hydrogen yields C2H2, and that is a endothermic reaction. We're going to put energy this time, or heat, or kilojoules, on the reactant side. Do you see it there? It's on the reactant side, R for reactant, by the way, instead of the product side. Why is it on the reactant side? Because heat is going in, or the big word is that it's being absorbed. Now, a lot of times they might ask you about breaking and forming bonds. So if you look, it says you need to absorb energy to break bonds. Anytime you break something, it's like karate chopping something. If you are going to break bonds, like Br2, and you break bonds, goes to Br plus Br, we're going to have to, you guessed it, put energy in. So heat would be on the reactant side because you absorb energy to break bonds. If I were forming bonds, the opposite would happen. The reason when you form bonds, remember, you're going out, 2 single elements, they're partying with each other, they're going out, they see each other, they meet from across the room, they want to become more stable, they want to get married. When they get married, they breathe a sigh of relief, and they go, ah, and they release energy. So energy, in this case, when a bond is formed, it is exothermic. So this is bond formation. please do not forget the words absorbed and released and how they relate to endo and exothermic. Okay, a few more math problems. A few more math problems. Um, Actually, let's take a break and then we'll do the math problems in the next segment.